Hey everyone, welcome to Cassandra Lunch number 101. Thank you everyone for joining us. We'll go ahead and get started.
Is my audio good?
Yep.
All right, cool.
Hey everyone, welcome to Cassandra Lunch. We'll give everyone a couple more minutes to file in and we'll get started shortly. Alrighty, let's go ahead and cut the music. Let me do some quick rearranging here. Alrighty. Hello everyone. Thank you for joining us for Cassandra Lunch number 101. If you guys missed out on Cassandra Lunch number 100, you can find it on our YouTube channel, youtube.com/AnantCorp. If you're watching this on YouTube, don't forget to like and subscribe, but also turn on the notification bell so that way you can get notified whenever we do go live or whenever our new video is processed and available, which is generally directly after and while the live stream is happening. Today's topic is going to be on IoT in Cassandra. Today's speaker is going to be Obioma Anomnachi, who's an engineer here at Anant, and he'll discuss how Cassandra and IoT can work together. If you're not familiar with IoT, it's the Internet of Things. And then he'll also discuss data modeling for IoT and how different devices may send data back to the cluster. Co-organizers for this event are Rahul and myself. If you're interested in giving a talk here at Cassandra Lunch or Data Engineers Lunch, our sister lunch, which happens on Mondays, feel free to reach out to me. My email is listed below, as well as if you're interested in sponsoring Cassandra Lunch or Data Engineers Lunch, you can reach out to me as well. And obviously, share the word, send your friends videos, get them to join. The more people we have live, the more interaction we have with the community, so we can pull out better talks as well. We are part of Data Community DC. Data Community DC believes in building an inclusive environment, so no matter your race, gender, sexual orientation, everyone is welcome, and we expect the respect to be given to all. Data Community DC is built up of a bunch of different organizations. Our sister lunch, Data Engineers Lunch, falls under Data Wranglers DC. If you're interested in all the various organizations that fall under Data Community DC, you can find out more at datacommunitydc.org. So what do we cover here at Cassandra Lunch? We cover everything that is Cassandra, talks Cassandra, plays well with Cassandra, whether that be open source Cassandra, enterprise level like DataStax, variants like Scala, Yugabyte, Keyspaces, Cosmos DB, as well as things in the ecosystem that play well with Cassandra, like Spark, Kafka, Airbyte, Airflow, etc., as well as some talks on DevOps related tools like Kubernetes, which we've given talks on Kubernetes and Cassandra, as well as Cassandra as well. If anyone's new here, say hi, hello. We're in the YouTube chat as well if you're watching on YouTube. Group rules, if you have a question, please do ask it, but be polite and courteous to the speaker. The speaker may have preferences in when they prefer questions, but again, this is meant to be a community, so please do share what you know with us, or if you have any questions related to the topic, don't hesitate to ask. Here at Anant, we design, build, and manage global real-time data analytics platforms surrounding Cassandra, Spark, and Kafka, so Cassandra is our bread and butter. DataStax is a partner and a sponsor. GW University helps provide venue space when we have in-person events. We also have some organizational and institutional sponsors. If anyone has any job offerings or is looking to find a job, feel free to drop links. We'll get them transferred to and from. Or if anyone has any meetups, hackathons, conferences, or classes that they would like to promote, feel free to drop links to those as well. DataStack Astra currently has a hackathon ongoing. I believe it's about to end. Apologies. So the third round is about to end, but the top 3 winners for each round have qualified or will qualify for the demo day. So there were cash and swag prizes to be won. So if you're one of the teams that ended up qualifying, congratulations. We hope to see who the winners will be. Anant is hiring. If you're looking for a full-time, part-time position, data platform operator, engineer, architect, you can find out more at careers.anant.us. Again, all Cassandra lunches currently happen at 12 p.m. Eastern on Thursdays. We are looking at having a more variable time slot so that we can cater to a worldwide audience, as well as data engineers lunches, which happen on Mondays at 12 p.m. Eastern. Same thing about the time frame. But again, next Monday, the 30th, is Memorial Day, so the Anant office will be closed. So we will be back for data engineers lunch in 2 weeks. All these videos are available on our YouTube channel, all the Cassandra Lunch videos, as well as all the Data Engineers Lunch videos. You can find the playlists on our channel, as well as Cassandra.Link should be your number one resource for all things Cassandra. We're in the middle of revamping it, pushing out new features, changing how it looks. Feel free to send us some input if you want to see some certain features on there as well. But all of these links here on Cassandra.Link are hand curated by the team here at Anant. So if you have anything in the context of Cassandra, you'll be able to find resources for that on Cassandra.Link. And Anant actually has also released our 3rd public runbook. So if you were able to get the first runbook and second runbooks, those are now offline, but we do have our 3rd runbook, which has now released, and we'll drop the link to that in the YouTube chat as well as the Zoom chat. And with that, we'll go ahead and pass it over to our speaker for today, Obi.
All right. Sharing my screen. All right, as you heard, my name is Obioma Anomnachi. I'm an engineer here at Anant. Today's topic is IoT and Cassandra. We're going to be talking about data modeling in normal Cassandra, data modeling in Graph Cassandra, and potentially we'll talk a little bit about the different communication methods that your IoT devices might use to send data to Cassandra, but I'm actually going to push that off until later while I investigate because I had an idea involving coordinator nodes that I want to look into more before giving a presentation on. I generally prefer to take questions in the chat. If you are on YouTube, some of my colleagues are watching the chat there and will post in the Zoom chat where I can see them. But also, if you are in the call with me, feel free to unmute and speak anytime we're moving between parts of the presentation. So when we finish the topic or when we're moving on to the demo, um, those are good times if you prefer to unmute and ask questions. All right, so starting off, IoT, like Arvin said, Internet of Things, it describes physical objects that have network connectivity, essentially. So all sorts of smart devices, your smartphone itself, all sorts of remote sensors, basically any data transference that used to be called telemetry now falls under Internet of Things. You can the IoT devices might generate data using connected sensors, onboard software if they're running. So things like edge computing devices might send data back, um, and device telemetry. And you may also have the ability to change those if you're using like actuators or smart light bulbs or things like Bluetooth speakers. You can change what they do in response to receive data as well. Um, IoT devices, they are very much a big data topic. They generate large volumes of data, high velocity, um, and they're constantly generating new data. Uh, IoT architecture, generally, your device layer contains all of your actual IoT devices and potentially gateways that sit in between that and your IoT hub. Your central hub holds data that comes in off the device layer. It does things like you can see in the picture over to the right. It might do real-time analytics, um, or it might just go into hot and cold data stores for later analysis. And then your insights section, your analytics engine, if you use BI tools or you're doing analytics or machine learning on that data that's ultimately from your IoT devices, that sits in a third layer off to the right. So using IoT and Cassandra together. Obviously, like I just said, lots of high velocity data, large volumes of writes, and Cassandra is great at handling that kind of thing. Basically, because Cassandra can handle large amounts of concurrent writes and scale out to handle even more, and also more storage, that makes it a good fit for time series data in general, and then IoT data specifically. Um, IoT devices generally send out a large number of messages that only contain a small amount of data. A lot of the examples talk about like temperature sensors, but something like GPS is only a small set of numbers. Generally, when you're dealing with IoT, you're not going to get a single message, like a single row with huge amounts of data in it. So even like a security camera that might take pictures will send back the pictures, and it might even have like some onboard processing, so that what you're actually getting back in the IoT hub is downscaled to be something that can be stored there over a long period of time. Generally, when you get your messages from IoT devices, you'll get the timestamp that the message was sent. And that makes it easy to query data by device or by date range. And then these characteristics also make it pretty easy to work with IoT devices as streaming data sources, although we won't really cover that today. If you're using Akka or Kafka, those are also pretty good for working with IoT devices or like Spark streaming. And then Cassandra also has customizable time to live and compaction settings specific that can be configured specifically to help with if you're working with time series data like IoT stuff. And then we're actually going to come back to these links. But essentially what they do is we look at data modeling, the normal Cassandra data modeling process, where you start with your queries and you go down to different levels of specificity in your data models, until you have your actual table definitions. But we'll look at that after we cover a little bit of how standard IoT data modeling works in Cassandra. So we're contrasting this to graph data modeling because graph databases are also pretty good for IoT data if you can avoid the pitfalls that are associated with IoT data in the first place. So data modeling for IoT in Cassandra is done with the standard Cassandra data modeling process. You're using tables, indices, materialized views. You start with your queries and you design your tables around them. And then the Cassandra specific things that you need to sort of keep in mind as you're dealing with IoT data. You want to limit the number of rows in a partition. Like Cassandra, if you have wide partitions, you lose efficiency. Generally, you want to keep partitions below 100,000 rows, but IoT devices can easily just exceed that. For example, if we talk about our previous example, that is just device ID, temperature, timestamp. So, if it runs every 5 seconds, you get if you get a row every 5 seconds, that's 17,000 rows per day. So you have maybe 5 or 6 days until you created a wide partition. And in order to avoid that, and devices that generate data even faster than that, like 5 seconds is not abnormal. Faster than that is also not abnormal. Some devices can generate data significantly faster than once every 5 seconds. And you also don't want to put the timestamp in the partition key because you'll end up with a bunch of one row partitions and it'll be difficult to query and actually get meaningful data out. So what you want to do in order to cut down partition sizes is split off portions of the timestamp or other data involved. So you can do things like you have your device ID, sure, but maybe that device is getting data from 4 or 5 sensors, and you have those split up into their own messages, into their own rows, and then partitioned also along the sensor ID lines. But the main way that you would do it is you would actually take timestamp fields. So maybe split it up by year, split it up by day, so that your partitions still have meaningful amounts of data in them and a meaningful divide. But also you can get useful queries out of them, but also they stay below that wide partition sort of boundary. And a lot of this is pretty easy to do using like basic math. So you can take like number of seconds in a day to get your total number of messages in a day, and then see how much you need to break that down by so that it will actually stay below that threshold. So it's possible that if you are not getting very many messages, you could break it down by, this is all the data for this year, this is all the data for last year, and put that in your partition key. But as you go lower and lower, you can potentially get more granularity, smaller partitions. It works best when the data stream coming in is constant. So like the example of one new row every 5 seconds, but that's not always true. So you also sometimes have to get more clever, splitting, potentially using AM, PM, splitting using custom time periods if you know when data is coming in, or potentially splitting using things like counters, like add in essentially a meaningless field that will, as data comes in, split your stream down into partitions that are still useful. And then the other thing that you might want to do, if you remember the diagram from earlier, it talked about a hot data store and a warm data store or a cool data store. And that's because over time, you're still filling up your database, and you don't always want to be buying more storage. Deciding what data is relevant and what data is not relevant is a big part of managing your database. So one of the simplest solutions is just to use TTL settings and window your data. Only the most recent data sticks around, everything else gets thrown away. But if you want to keep that historical data, which you often do, there are ways to do that without just continuing to buy more and more storage space. So something you can do is you can aggregate or combine all the measurements for several rows. So both aggregate in the means of like mean or average over a certain time period, but also aggregate as in just put all of the actual measurements that you want to keep into a single object somewhere else that you can later parse in order to get out specific data that you want. So you could take all of your data for a day and then combine that into a JSON object or something or a string and put it in blob storage or some way to keep those in a table where queries are made by day. And then if you want to further break that down, you can do that on the application or in the analytics side. And that's how you would create something like a warm data store, where your hot data store deals with your most recent data, your most important data, something that you're always querying. It's your most valuable data, essentially. Whereas historical data, it gets warm over time, it gets cold, et cetera, et cetera. So warm data, you still want to be able to query sometimes, potentially do analytics on. But over time, you can even end up with cold data, which you maybe just want to stick somewhere and not touch unless something forces you to. And then one of the solutions for that is potentially to take the data from your warm data store, aggregate it even more, or store it in some efficient storage like files, like store it in Parquet files or something. And then move those off Cassandra entirely so you can make use of cheap storage like S3 or Google Cloud Storage or something like that, somewhere where your data can sit. And unless something specifically needs you to go in and find data in that sort of state, then generally it just sits there. So you know that you have your historical data, but also it doesn't need to be taking up space on your Cassandra cluster that you're paying for every month. And then processes like these are easy to manage via Spark or DSE Analytics if you're using DataStax Enterprise. And then when you're moving stuff down your data tiers from hot to warm to cold, those are also a good time for analytics or aggregation. So we talked about potentially using like averages or means, that sort of analysis, but also larger analytics can potentially take place at that time. All right, and then stepping back for a moment. To look at our sort of data modeling examples. So firstly, concerning time series data, we map out our entity relationship, and it has groups of sources that contain individual sources that generate specific data points of a specific metric. So your temperature data point would be all the way down here at metric. Your data point, including the timestamp when it was generated and the actual value, would come up here, and then they'd be associated with a source, and then that source would be associated with a group of sources. And then you have your queries laid out here. So the queries that you might want to make here are all the data sources in a group, all of the metrics on your cluster period, if you're trying to get an idea of, lifetime averages, that sort of thing. Split up by source, maybe split up by metric values, or split up by statistics. And some of these things you might use separate tables with different types of concurrent insertions or materialized views or indices. All of these sort of come into play here. And then when you're coming up with your logical data model, you don't assign actual types to your to all of your fields, but you group that data into fields. What do you actually want back from your query? And then also decide on what your partition key is and what your clustering columns are and which way they sort of point. So you can see when we are querying by source, we can do it low or high, depending on which way the source clustering columns. So in this group, which way do you organize your sources? And then you can also see your time series data biometric, and all these other things. And then when you build out your actual data model, you assign all of these actual types so that you can actually build your table definition off of them. And then sensor data modeling specifically for IoT is actually very similar. You can see we have our sensor, it generates records of type, temperature, and then there's information about the sensor and also information about the network it's connected to. And this sort of gets into what other information we might want to keep track of. And this is something that graph data modeling will eventually specialize in when we talk about that in a little bit. But you end up with your same map of queries, map of tables in your logical data model, and then in your physical data model with everything needed to actually do a table definition. And then speaking of graph data modeling for IoT, you can use your graph, you can store that IoT data in graph databases. It's specifically useful if you have a bunch of interrelated devices and infrastructure, and you can use the complex queries on that graph to then know things about the relationship between your sensors and their infrastructure. So you can still query for specific measurements related to a specific device, the same type of queries you might make of your standard data model without graph. But then you can also get an idea of what other factors are related to your device. We'll look at an example in a little bit. But you could do things like use the graph to keep track of what analytics processes later on your sensor's data is actually feeding into. And then if you write your query properly, you can show which processes or which teams in your company might be affected if the sensor were to break or go offline. You can also use the graph database to look at the non-measurement related aspects of devices, like the data model previously for the sensor data model that we just looked at had location and longitude and latitude for each sensor. And even if that's not what the sensor is measuring, it might be useful to know so you can lay them out on a map in your later data analytics phase, or do other things with them. So things like battery life, things like manufacturer, things like connection to your other devices. And then we're going to look at this article, which is actually mostly for Neo4j, but the same principles sort of apply to DSD graph. But essentially, your definition of your thing in Internet of Things in a graph database has all these different fields. So in this case, they show relationships to vendors, relationships to specific modules within the device, manufacturers, networking stuff, specific sensors that will be giving back data, power sources, downstream applications or upstream applications that are sending data back to your device, and then departments at your company that are using them, as well as categories of IoT device that are sort of getting defined here. So you can see some of these properties that they define. A thing or an IoT device has device ID, name, latitude, longitude. Other nodes also have that. But if it's powered by a battery, you can see data like life start, life finish, when the battery was installed, potentially things like battery percentage. So you can query and see how close, this sensor is going off in 1 day, this sensor is going off in a week, this sensor is going off in 3 weeks, unless you replace the batteries, et cetera, et cetera. Solar, they specifically talk here about installation date and inspection dates. So potentially it's just this sort of, the graph is sort of a central hub, depending on your actual amount of data that you end up wanting to store in it. A central hub for all sorts of interrelated things in your company process, so that you make sure to keep everything running. And then you also define all these different types of edges. So from vendor is composed of sensor, heat and temperature sensors. And then we also talk about different types of queries. So this query is everything connected to this specific thing. So all of these other devices potentially, or the sensors that compose it, or the manufacturers who made stuff in it, of course, the power source. So to get an idea generally of what's going on with this specific device, you can query that way, but you can also query in these other ways, in which case we're talking about departments, which are 2 steps off from your actual device through the application layer. And you can actually see this department's using data from this device, this department's using data from this device, et cetera, so that if devices are planned to go off, like I said, if they have battery life or maintenance requirements or things like that, you can tell which teams might be affected ahead of time. And then the third type of query that they're talking about, return all the battery powered things, and then also give the expected end date of their battery life. So you can sort of predict all these things are going to go offline next week or in 2 weeks. And you can potentially also use this to schedule your data tiering. You know, remove this, all the measurements that came in from thing 8. Because thing 8 has died, we're not going to be receiving any more measurements. Move that off to somewhere else for specific like analytics and querying, and remove from the graph. So there are all these sorts of advantages that graph data modeling might give you over over normal data modeling, but you still have to take into account all of the same sort of issues. Potentially, you might have stuff like TTL in your graph database. You might have some sort of bucketizing going on. And basically, you just want to try to keep the advantages of your graph data modeling without causing any sorts of super nodes or super edges, or even properties within those to get too full of data to the point where, because in DSE graph everything still is underlined by Cassandra, that Cassandra will have trouble querying that data in the future. All right, we're going to move on to the demo in a little bit, but this is a good time for questions if there are any.
No questions from YouTube.
Okay, cool. So our demo is actually sort of based on, if you remember from a previous Cassandra Lunch talk on the Grafana Cassandra data source, it specifically was meant for visualizing time series data. And so we're going to sort of repurpose that to look at some time series data, and then also see it potentially bucketized, how that queries are different for that, and then also potentially windowed. And we're not really going to look at the data tiering today, but if we can see, how bucketizing might help you with that, then we should be good. All right. So because this is based on that same Cassandra Grafana example, we are going to bring up our Docker container. And what's actually happening is, check this out actually. So there is a utility that generates data and sends it to Cassandra in one Docker container. And then there's your actual Cassandra in the other Docker container. And what this program actually does, when you start it up, it waits until it can connect to Cassandra, and then it creates a key space, creates tables. In this case, test.test is our normal non-bucketized, non-tiered, just like completely standard IoT table. it is literally partitioned based on the sensor ID and nothing else. So over time, you would run into that issue where data keeps coming in and your partitions are getting wide because it's not split off in any way. And then we have a bucketed version of that same table. And then later we have a windowed version of the same table that uses TTLs in order to keep the actual amount of data in your table low. And then something that we just sort of skipped over that you can actually do with this, because we have these aren't actually like simultaneous submissions, but they might as well be. And something that you can actually do with that is you can set up two of your tables in such a way that if you remove the timestamp from the primary key in one of your tables, the insert into one table where the entire row with the new timestamp and the same sensor ID, but a new timestamp gets uploaded into your Cassandra table. You get one new row in the table, and then in the other table that gets uploaded that same data, it becomes an update rather than insert, even though you're using the same, because all updates in Cassandra are actually upserts. But you can use that as an easy way to keep a table with only your latest data coming in from each sensor in it, because your sensor ID is no longer, your timestamp is no longer a unique an identifier of a unique row. So your new data comes in and it just overwrites. So you could keep a table that shows the latest values coming in from each sensor, while also keeping a table that shows all of your data coming in and stored historically. So I'm going to open CQLSH. So this demo uses CQLSH. So we're just using CQLSH to submit our data to Cassandra. Other methods that you might end up using for this are applications with Cassandra drivers in them, potentially something like Spark Cassandra connector. I had an idea, which I want to investigate more before actually trying to talk about it in great detail. But essentially, the way that Stargate uses Cassandra nodes to facilitate requests, or did I say Cassandra nodes? I mean coordinator nodes, to facilitate requests into using its various APIs. There is potentially a way that you can set up a coordinator node on one of your external devices so that it can send data, but because there's no actual storage on your IoT device, then Gossip and the Cassandra protocol makes sure that that data goes and gets stored on a node with actual storage. So potentially a way of having your IoT devices be nodes as part of your Cassandra cluster, even though they don't have very much storage. And you wouldn't want to, rely on storage that's based on an IoT device, even with, Cassandra replication. All right, so the first thing we want to look at is just our standard table. Test.test. You can see we have all these rows. There are only two sensor IDs and they're very slightly different. It's just the 0 and 1 on the end here that distinguishes them. But you can see it's actually grouped them, all of the sensor IDs that end at 0 here, all the sensor IDs that end with 1. Because timestamp, or I guess it's registered at here, it's the timestamp column, is part of our primary key. It's the clustering column. You can, if you provide a sensor ID, also provide a range for that and get data within a particular window. And then we can also look at the windowed version. And you can see we're limited to like 10, 12 rows in this table because the time to live is set to like 20 or 30 seconds. So even as new data comes in, old data expires, you keep only a window of your most recent data in this table. But it's not the same as that previous thing that I was talking about where you update data into each row. You can keep a number of recordings from each sensor in this table here, but only the 5 or 6 most recent rows will exist in this table at any given time. And then we can also look at the bucketed version of this table. And what I've done here is every minute. So this is not how you would actually want to do it in production. But because of the small time scale of this demo, it works to just have a minute field. So all of the rows that came in this particular minute are bucketed together. And to reference them, you need the sensor ID and then also the minute that they came in. So in order to get all of your historical data, it's going to require a number of queries. And then also as the minute field loops, because it'll go from 0 to 60 or 0 to 59 and back again, you'll actually get overlap, which is something you wouldn't want in a production database. So it's generally important to have steps that go all the way down to whatever your smallest bucket is. So you might want to include both the year and the month, and the day and the hour and the minute into your bucketized field or in a number of different fields in order to distinguish your data and make sure that you're still not getting wide partitions in the future or overlapping your data with newer data inside the same bucket. And you can also query bucketed data. Using, in this case, our sensor ID and minute equals, say 39. And we can see we cut down the number of rows. That is strange.
Yeah, I think it was just
that's more normal.
Register. Like if you look at where it says more and then select.
Oh yeah, I was still in the previous query. Yeah, so you can see you cut down to your specific bucket. We only have 10 rows in this bucket. It will definitely stay lower than 10,000 rows. But the original test.test table potentially will run into that issue in some matter of time. This one will in a much longer time, 60 times as long, because the buckets are overlapping and not defined perfectly. And then the window, of course, will stick to its 10, 12 rows, no matter how much time goes by, but it won't store any of that other data. All right, more time for questions. I can potentially, well, no, we already went over a little bit, and I do want to save more discussion of the sort of communication of IoT devices to Cassandra for a specific Cassandra lunch on those later on. So I will end it here and pause for questions.
I have a question, Obi.
Yes.
So you started the presentation talking about how Cassandra is a good fit as a database for managing the input and storage of IoT data. Do you, in your reading and preparation, in your experience, do you think that there are companies who may struggle with the proliferation of data that is generated by these IoT devices? And do you know about, what are some strategies for deleting that data? Just if you could talk about that for a second.
Yeah. So, well, I want to say yes, potentially. Well, part of it is that it's difficult to get to a point where you're dealing with huge amounts of IoT data and you haven't put in any effort in order to manage it. So I think that companies who find themselves in that position, they sort of have some mitigation steps in place probably already. But if they're finding they're having trouble with these historical process or the accumulation of historical data, so we did talk a little bit about your data tiering earlier, and that's a potential solution that you can set up. Use something like Spark or whatever other analytics processes you have in place to move some of that data out of Cassandra or wherever the primary data store is, your hot data store, and aggregate it and store that data in some lesser data store somewhere else. So you downgrade the importance of that data and you move it out of your primary data store. And that is the sort of like central core around all of the potential solutions. Basically decide what data is definitely important and needs to stay where it is in your hot data store where you're going to be querying it all the time. And then find some solution, potentially using Spark or other analytics tools, to differentiate that data from your other data, and then figure out what you're going to do with that other data. So one of the solutions is to potentially, set time to live for all your rows when you're inserting them, so that your old data just gets automatically deleted.
Mm-hmm. And so I think one significant thing that you said, which is kind of that's really the point that I was trying to ask is that IoT, when you were talking in your demo, it does create a ton of data, but the data that it creates is just a very small amount of data, or it takes up a small amount of space. So what you're saying is that it would take a long time to develop or to even if you didn't have a mitigation strategy, it would take a long time for that data to become a problem. Is that correct?
Well, potentially.
Okay.
Well, we talked earlier a little bit about how, 1 row a second is a sort of common amount of data. So even if that individual row isn't holding much data, even in, a day or a week period, you can still start accumulating data to the extent that it starts to cause you problems. Not that you're filling up your entire Cassandra cluster necessarily, but potentially that you're causing problems with wide partitions, which will sort of decrease the efficiency of your Cassandra cluster over time.
Got it. Nice. Thanks.
All right, I'm not seeing any other questions from the YouTube chat. If anyone has any questions on here, feel free to speak up.
All right, if there are no questions, I will pass it back to Arpan to close out.
All righty. Thank you. Thank you everyone for joining us for Cassandra Lunch number 101. All these videos are available on our YouTube channel, youtube.com/AnantCorp. So if you're watching this at a later point in time, don't forget to like and subscribe, and also turn on notification bell so that way you can get notified when we do go live the next time, as well as whenever videos are posted, in case if, again, you're in other parts of the world, so you miss the live events, you can watch them and get shown in your subscription feed as well and get notified with the notification bell. And with that, we'll go ahead and wrap up for today, and we will see everyone next week. Take care.